Hey guys, welcome here. I'm Sunay Tripathi. I'm one of the founders and CTO for Pluribus Networks. Guys, I'm not a networking guy, right? If you go and Google me, I build server OS, right? I build virtualization in servers and all my life, basically, right? So we're not out here to do more networking. The goal here is to figure out what do we do with applications and virtualization and servers, right? In some sense, I want that stupid switch that did nothing in the rack to disappear, right? I want it to become a server switch. I want to put a server OS on top of it. I want to put applications on top of it. So like Dave said, it's all about apps. But apps don't run on their own. I mean, we are working on apps running in real cloud, but really today they need an OS and a piece of hardware underneath it, right? That's what we do. We're trying to figure out a best platform, best hardware, best everything to actually open up networking. So having said that, guys, I do suffer from some ADHD. If I'm the only one speaking, I'll speak very, very fast. Nobody will get anything, and it'll get very boring. So you have to stop me, and you have to, this is about discussion, and this is about figuring out where are we going, right? So I'm going to skip through a couple of slides, but reality is, this is what Dave was talking about, that, we are building a same story that was repeated some time back, right? We are repeating the same story. Now, keep in mind, the iOS story is more recent history. We have seen that. We all saw that. But the same history played out in the world of Unix and servers 10 years, 15 years back, 20 years back. Mainframe went to desktops and servers and dual socket servers, which went to Intel's dual socket servers, which went to Linux, and so on and so forth, right? So we understand this story fairly well, right? The interesting part is if you look at the networking picture, right? And let me go through this, right? This is really evolution of networking today. You're building Ethernet fabric, right? Giant boxes with just shuffle packet. Don't add any value to application. You can't debug these boxes by themselves, right? There's no way to figure out why your networking doesn't work. So what do? You put a monitoring network, right? Oftentimes, as we go from 1 gig to 10 gig, these monitoring networks tend to be more expensive than actually the physical network, right? The cost of Ethernet is plummeting down. The cost of monitoring network is going exponentially higher, right? We need services, right? What are these? Typically, x86 server wrapped in sheet metal, sitting in your network, basically, right? Why can't these just be software? Then, none of this actually achieves anything on virtualization front. So what do we end up doing? We said, look, let's hide this mess in the closet, and let's create overlay networks, basically, right? Now, this gets really, really very interesting, right? The complexity here is amazing underneath in the world of physical network. So we call it underlay. We hide it under the covers, and we create the shiny world of overlays, right? Everything just magically works, right? Reality is doesn't, right? Let's see at least. This is going to be interesting. Okay, let's go deeper into this. So few things that are worth pointing out, right? Because this is our mission. One of the things, if you look at iOS and Android, they achieved. Why does a guy who wrote Angry Bird was able to write an app on that cell phone? Because he wasn't forced to deliver your Bluetooth stack or your Wi-Fi stack or a 3G stack or a 4G app or LTE stack. The platform provided you that capability, right? Me as an app developer could write apps on that platform without worrying about what was the connectivity, what was the topology. I could always assume to be on network, right? And be connected all the time. So to bring applications into networking, we have to provide the same capability, right? If the guy is worried about L2 and IP and VXLAN and tunnels and ports and topology. Now, like, guys, remember I said I'm not from the world of networking, right? But the world I came from, those guys don't understand this shit at all, right? You ask them about tunnels. Tunnels are always done by that guy at the other side. We have one ex-kernel developer sitting here. Ask him, who was his tunnel peer? The guy who did the tunneling. Do you know who was it? We don't know who that guy was. I ran the entire Solaris grid, basically, right? And yet, I can't remember for the life of me who did tunneling in Solaris. Who was there, right? A typical kernel guy is dealing with just TCP/IP and Ethernet, right? And applications coming in assume IP connectivity and socket. That's all they know. I'm going to make a socket call. I'm going to connect to the other side. I have the IP address. Maybe I have a domain name or the box name, and that's it, right? So if you start teaching those guys VXLAN and tunnels and IP and L2 and whatever and BGP, it's not going to work. And more importantly, topology independent. If they have to understand how the network is built to get their apps to work, it's not going to work. So that's one thing Netvisor does. Netvisor is trying to provide the same paradigm out to people by saying, look, don't worry about the network topology, right? Think the network as a network. The connectivity is there. There are some experts who will build the fabric using L2, L3, or VXLAN, or whatever it is, right? But once that fabric is running, it's a full-fledged server. What you come on switch, you just program using C, Java, Perl, Python, whatever you want. You don't worry about the network protocols. You worry about what you're trying to achieve. You worry about flows. You worry about, who talks to who, which VM talks to which VM. I want my vport list. Did this VM migrate from here to here? When was it created? Who does it talk to? That's the stuff I need. And we have applications guys who know how to code that. So you have to decouple the two, right? And then the third part comes in. This is the first time we are opening up the switches for applications, right? Obviously, the guys are not going to come and write their own apps. There are bigger guys out there which are doing it. But for mass market, you have to follow the same paradigm as a server OS, right? You have to follow the same paradigm by saying, I'm going to deliver a bunch of the apps myself, right? When you install a Linux, it comes with a browser. You don't have to use Firefox. You can go and download Chrome. Same model, right? So having said that, let's look at a little bit deeper, right? What is the networking paradigm, or the switches, as we call them, look like today? This is what a legacy switch was, right? If you look at it, the switch chip was very powerful. The guys who built the switch chips were building very powerful ASIC. It would learn, it would switch at 1.2, 1.8 terabit per second, and it would actually do the job very well. There was no room for software there. The fact that I took two people and plugged into the same switch, it will automatically start switching, right? So where is the control? Well, maybe he and he can't talk. They hate each other. I don't know if you guys do, but maybe you do. So if you actually
he doesn't really hate anybody.
He doesn't hate anybody. So maybe he is the guy. You plug him with him, right? They shouldn't be talking. At least there needs to be a software control. There needs to be something in there which says, yes, he's allowed to talk. Maybe if even they're allowed to talk, I need to know that they were talking. I need to know what rate they were talking for capacity planning, for analytics, for debugging stuff. When he can't talk, I need software in there to figure out what is going on, basically, right? So what we end up doing, right, we ended up going down the path of building a simplest form of server, right? Keep in mind, the old switches were like this for cost reason. There was no reason to put a heavier processor or more memory in there because A, they were not doing anything, and B, they were expensive. At the end of the day, it's also about money. So today, if you go and try to put together a lowest cost server, what is that server today, right? You guys use Chromebooks and so on and so forth. They're built using Intel Rangeley class processor, right? 4 to 8 gig of memory, right? And that is your cheapest form of server today, cheapest form of compute today, right? It's not Freescale anymore. Buying 2 gig of memory is more expensive than buying 4 gig of memory. So that's the control plane that most of the ODMs started putting together, right? So if you look at the modern switch, this becomes a modern switch. The control plane is an Intel Avaton or a Rangeley processor, 8 gig of memory, connected via PCIe, right? Now, this thing is not an embedded platform anymore. Remember, Rangeley is a quad-core processor, so is Avaton. It's a VTD-capable box. I can run a full virtual machine in here. All of you guys are running laptops which has processors more powerful than this, right? So the moment this comes in, We are out of the world of switches and embedded systems and so on and so forth. We are in the world of, let's put a full-fledged server OS here, right? Let's put virtual machines here. Let's run 500 threads of control plane processing here. Entire switch gets memory mapped into your OS, right? Over PCI, because we know how to do that. We have been doing that for only 20 odd years. And we can go and literally write every register a gazillion times a second if you want to, right? Changing a flow is reading a register, looking at some code, and rewriting that register. That's as simple as it is. Same idea as the SDN as it came around, that I need a control plane separation from data plane. The only difference here is I need my 500 threads in there who can write a register in sub-microsecond to do that, right? So we tweaked that SDN design a little bit, saying that the controller living in a separate box doesn't make sense, especially if the control plane bandwidth is not there. We went bare metal, right? We said we need our 500 threads to go into the switch chip and manage every aspect of that switch chip. That's what Netvisor does on a single box, right? Then we went further and said, look guys, if we can actually put more application on this, there's a huge cost saving, right? So why don't we ask the ODMs to build another box, which is, heavier in compute, goes up to 1 terabyte of main memory, has PCI Express, PCI Flash for storage, and these are still switches. At the end of the day, if you look at it, this box right here, this is the box right here. Dual socket Intel processors, the best money can buy if you want, 1 terabyte of main memory if necessary, PCI-based flash, right? And this can run hundreds of virtual machines which have direct access into the switch if necessary, right? So now you have the control plane matched with application platform that can actually go and program the network. We're missing one piece. This still allows only one box to work, right? Typical network is built of a lot of boxes, a lot of switches. Each rack has typically 2, right? You want to deal with the network, not individual boxes, right? So that's where we end up going a little bit more distributed, right? So, and again, these are things that we didn't invent. Serverworld had done this for a long time, right? We just bought that technology into the switching world. How you do distributed systems. We've been doing this for a long time, so we can take any type of box. It can be your canonical white box, it can be your blade boxes with switches in there, it can be your Trident 2 boxes, it can be Alta boxes, whatever you want. But the whole goal is the Netvisor runs as a distributed OS on top of these boxes. It's a plug-and-play architecture. It allows you to have VMs on top, and the VMs come in many flavor. We can run KVM style. A lot of people who want to do heavy I/O from these boxes, KVM is too slow for I/O. So we're working with BSD guys. We did a lot of contributions there to get the Beehive hypervisor going. In fact, we are the people who bought Linux on Beehive, basically. And we are doing containers as well, basically, right? So let the apps come in whatever forms you want, and let them use whatever API they want. C, Java, Perl, REST, whatever you want. But one interesting thing is, all our APIs allow you to program the network. They always have one extra argument, which is called scope. Am I dealing with the local box, or am I dealing with the network, right? The moment you say scope is fabric, the job of the OS underneath is to guarantee you that you're synchronous across the entire fabric. If the fabric consists of 50 or 100 switches, we make sure the same operation is guaranteed done by the time call returns. Either you get an error code, in which case none of the switches have it, or you get a success, in which case all switches are guaranteed to have it, right? Very different than scripting, guys. This is not scripting, right? Because typically I can write a script to go and do this on 50 boxes. What do you do when 10 boxes succeed in a row and 11 boxes fail? How do you back out of that? Your network is in consistent state, and especially if you're trying to schedule flows across your multipath network, you're gonna get into problems. So we really need a synchronous way to get into the entire network. And again, like I said, these are very open protocol. We use 3-phase commit and stuff like that. Things which were written in SIGCOMM papers in 85, 86, when I went to school. That's when we were reading those things, right? So few other things we had to do along the way, right? Again, we can't go and assume that the world which was used to dealing with legacy networking will start writing code and start deploying applications from day one. They're used to using CLI, they're used to doing L2, L3. So it's very hard or a losing proposition when you go in front of someone and say, I want you to give up everything you have, and I want you to use something else, right? Imagine all you MacBook guys, I take away your MacBook and say, you're going to go to a Chrome. You're going to fight me. You're going to nail me down here and literally pummel me to the ground if I do that. I'll do that.
You might be pretty happy if you got a Chromebook. I don't know.
So we gave them full L2, we gave them full L3, we gave them CLIs, we gave them UI, and we're built out of open source, right? We contribute a lot to open source, and we take a lot from open source, right? So like L3 all comes from Quagga and so on and so forth, but we are capable of building stuff where none exists to give the user full experience. L2 stack doesn't exist in open source, so we built one, basically, right? But the whole goal is a typical rack, two top of the rack switches in a HA fashion connected to spine. You want to drive this architecture across the board, right? So typically what we ended up doing is that we do that. Once you got the basic networking or topology going, everything becomes one fabric, one logical fabric to manage, one logical switch to manage, right? So from OpenStack perspective, this appears like just one logical switch with a lot of ports. You can manage this from any box. One interesting thing, we don't have a master-slave architecture. It's pure distributed peer-to-peer, right? So as long as a single box survives, it doesn't have to be the spine boxes. As long as a single leaf box survives, you can resurrect your entire fabric, right? So you want to add more rack, bring the next rack in, plug it, and say fabric join. Done, walk out. You don't have to redo the configuration. You don't have to worry about anything. A box dies, unjoin it from the fabric, put a new box in, fabric join, back online, right? So resiliency has to be built in, right? Remember, if you're going to change someone, you have to give them incentive to go to the new architecture, right? Incentives are, money is the incentive, right? So if you go down the path of I'm just going to make it cheap, sure, the guy who's paying, who's writing the check, it's an incentive for him. But the guys who are mostly users, it's not an incentive for them, it's more work for them. So the guy who's the user, who's actually deploying this equipment, you have to give him incentive to go to this new architecture. Resiliency is an incentive, ease of management is an incentive, and application on switches which help him do his job better is an incentive. That's what we are after here, right? So we go down the path of saying, okay, what are, now that we got L2, L3 going and we got the fabric going, what kind of applications we can build here, right? One simplest one is in a virtualized environment, how many VMs I got? What are they doing? Who do they talk to? Why do they exist, right? So typically, we go down to application level analytics. Now, this is an overloaded term, guide. When people say application level analytics, they don't even know what they mean. We go down, for us, it's very simple. When you say application level analytics, I want to see every TCP connection, down to that level of detail. When he says, I can't get my connection through, I want to see why. Where did it fail? When he says it's slow, I want to see why is it slow, right? So that's the level of detail, and I'll go into the demo, guys. I'm just gonna, because there are a lot of new guys here, I just went through some level setting, and then we are gonna jump into some of the demos. So which client talks to which server, what is the service, what is the state of the connection, what is the average latency that is seen. So we built a big data app here.
So can you do application mapping off of that? Because I've found that many sites can't even tell me, okay, we're delivering some service, which servers actually are used by that service?
I did not pay him to ask that question. I swear. I'm going to show you the demo exactly.
Probably on the next slide.
Yes, we'll go through all this demo, basically, right? That's the whole goal here, right? That nothing becomes hidden anymore. Everything becomes visible, and everything becomes open, right? The whole goal is that, keep in mind, at least my experience has been, I was blissfully unaware of networking till networking became a problem center. Like I said, I came from server world. We were very happy with servers and applications and a lot of money flowing into that and whatever. When we went virtualization, we became aware of networking, not because it was a cost center, because it became a problem, right? So networking is not a big spend. Nobody out there is looking at reducing their networking spend as much, maybe telcos are, but bulk of the people are okay with that. What they're looking to reduce the spend on is my server, my VM, and my application, right? And I wish I had that chart before, but if you look at a typical company, and you can Google this, your hardware spend, networking is maybe 15% of your hardware spend. And your hardware spend is maybe 10% of your total application spend, right? Applications is where the guy is spending a lot of CapEx and OpEx. So you have to figure out how to add value to that. If you can help him add value to that, the guy is happily using this technology, right? So the next thing that comes in, okay, I can see all this, right? And by the way, guys, this app, we sell this app. It's not a simple app. It's really a big data app on switches, because each switch is collecting all these analytics. And when you're running the queries, we go and assimilate the information from all the switches and present you the answers, basically, right? So this app is actually heavier than the platform it runs on, basically, right? But the more interesting problem is when we build it, typically by the time you see a problem and by the time you grab the network guy and say, hey, I got a problem, the problem fixes itself, right? I have seen this in my entire career. Every time you go to someone and say, hey, there is a problem, by the time he debugs it, it's all good. The moment you walk out, the problem is back. So we built a time machine capability into this. Everything is recorded, everything is memory mapped, but we put it on, once we exhaust the memory, we put it on disk as well, allowing you to go back in time, right? And analytics comes in three forms: network level analytics, virtual machine level analytics, and connection level analytics, which is application level. So we go look at everything. Was there congestion on the link? Was link dropping packets? And you can go back in time to see that. If it was, well, here lies the problem. But then you need to know, why was the link dropping packet? Let's look at all the flows that were using the link, right? Maybe someone was doing a big video transfer, and that was causing other flows to drop packets or have higher latency. And that is the key, guys. How quickly or how long does it take me to determine these things, right?
That sounds like a lot of data. Where is that stored, and how long is that stored, and how do you get access to it? Because I think in most consumer networks or most enterprise networks, right, the idea that, like that amount of data, you might be able to hold that data for like 6 hours, 12 hours, 24 hours, but that's awfully deep.
But that is exactly the key point here. You asked a very smart question, basically, right? So these boxes, which are equivalent of bright box, ODM boxes, basically, we don't do much in this. These are branded boxes, nothing else. They come with 8 to 16 gig of memory, right? Very limited storage. Enough, based on how many connections and all those kind of things you're doing, enough to maybe log 6 to 8 hours, 10 hours worth of data, basically, right? But then at least you have that level of time machine capability that, at least I don't have to take snapshot when I run to him with my problem. We can go there and you can say, hey, let's look a couple of hours back, and we have that.
Sure.
Right? But these are full-fledged servers as well. So it's very simple to write me a shell script or a cron job. Where every hour I dump all the data and move it to an actual server with a lot more storage, basically, right? And we build code around that, you can export this out in CSV format, whatever format you choose, with whatever delimiter you want. So you can actually move the data out of these switches very fast, right? A lot of people don't want to do that. For them, we build these bigger boxes, right? Where now you have a terabyte of memory if you want, and you have a Fusion IO 10 terabyte of storage. This guy can record data for a year, basically. Right?
So you're just recording flow data and records rather than raw data?
Exactly.
Okay.
There's no. Now, if you see some anomalies, if you see a problem with your flows, if you see a problem for compliance reasons, for security reasons, and we have customers who are using this, school is a good example, right? A lot of schools these days, someone's laptop got broken into, right? With a virus on there. The kid is running around somewhere between his classes. You don't know where he is in your campus. So first of all, before you block that kid, you have to do two things. You have to prove that his kid, there was real virus on it. So on these switches, you actually record, people are doing this, where they record 10 minutes worth of actual flow data at multi-gig rate, mark it as here's my PCAP file with whoever's laptop, and then they create another flow which shuts down the laptop, basically, right? So if you look at, the analytics allows you to take action as well because you're on the switches. So all you do is vflow create, name, test flow, or whatever guys, scope fabric, source IP, blah, 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 and action, instead of copy to CPU, you can say action drop. Doesn't matter where that kid is in his network, which class he's in, he's not on network anymore.
Can that be dynamic?
So this is effectively fabric-wide installation of a TCAM rule.
Yeah. That, at the end of the day, we're not doing much with the TCAM. We're using the same TCAM, right? The key part here is we can insert 1 million rules in a TCAM, right? The way we do that is by using the software as a bigger table, right? So we can run a network with 1 million L2 entries because we don't depend on actual L2 table. We use the hardware table as a cache, right? The software tables are a lot bigger, right? Anytime you have a miss,
You punt to the CPU.
punt to the CPU installs the right entry.
So it's
control
conversational learning.
Guys, your laptop is doing that while you're talking, literally million of times a second. Your PowerPoint, when it starts on your laptop, what do you think it's doing? It thrashes the VM system like anything. It's trying to hog every page out, right? And this
That's why it's so slow. Thank you.
exactly. Right?
Now, how do you capture the data about the application flows? Is it NetFlow export or is it SFlow?
Guys, NetFlow is so 80s.
Just asking. How do you
And it's
gather
not
that
real
data?
time.
And it's not real time. I'll show you in the demo, actually. When we get into the demo, we'll go through these details. That's exactly what I want to go to. And then this is, again, beating the same horse, basically, right? That or it's not based on tap. We are the switch. Packets are flowing through us. And by the way, you can take other guys' switch and mirror all the traffic to us. We'll consume that and pull that into our analytics as well, basically, right? So the whole point here is that, you don't need taps, you don't need probes, you don't need other stuff. All you need in your rack is switches, servers, and storage. Maybe storage is sitting outside the rack, but those are the only physical devices you need your network.
So
right?
the example you gave just a moment ago of the the student with the wireless, that's really more of a campus networking situation.
Sure.
Do you see a place for your product in a campus environment, or and where? I mean, I wouldn't imagine it would be at the access layer, but I mean, do you see that in an aggregation role in a campus network?
You got it. Aggregation layer is where people are putting it. But, the access layer is also starting to open up, right? They're all putting Intel Ranchly processors and stuff like that because that's the cheapest form. So Netvisor has many form, right? I mean, think of, your standard Linux. It runs on your cell phone on a teeny processor. It goes on your laptop. It goes on a dual socket server, and it goes on a bigger server as well, basically, right? The hardware provides the capability on what it can do, but the code doesn't change. So we are kind of that, like.
But I mean, do you have something that's just gigabit frontside ports?
Yeah, So I'll answer that question, and maybe Alessandro, if you can actually make a note of this, and when you go through all this stuff, where there's a go-to-market also, right? I mean, do you want to address that right now, or do you want to address more data center and 10 gig and 40 gig and 100 gig right now, and virtualization? So currently we are addressing a lot more on the data center side, right?
Sure, but that's where everybody's focusing with all the SDN solution. I just thought it was interesting that you kind of had a campus use case there.
We actually got pulled into a bunch of campus use cases, right?
For the visibility and analytics.
For visibility and analytics and fabrics.
Okay.
Right?
So I could potentially see this being useful in the wide area as well for very specific things, given your buffers are deep enough to handle the wide area traffic.
So we
exactly the same types of applications, but on a much more granular scale.
So wide area also requires some more applications, protocols, and whatever. So we don't go there directly. We have partners like VeloCloud and whatever. So they are building their wide area network stack on top of us. And together we go into wide area network deployments, right? And you'll see a lot more. This is, again, a platform which allows a lot more to come on it, right? So the case that we are also starting to see quite a bit, and we are trying to address, is what we call the server virtualization or overlays, right? So today what ends up happening is that you're running overlays from server, right? I mean, and I can give you an example here. This is typically your typical deployment. The overlays are running from servers, basically, right, from the hypervisor, and you're building tunnels between hypervisor, right? One of the biggest problems is too many tunnels and so on and so forth, and you're running tunnels in software, right? So what if we move these tunnels out of the servers and actually put them on the switches, right? And you run switch-to-switch tunnel, right? Keep in mind, everything in our fabric is visible to us, right? Everything is a vPort. Every time we get a miss, it comes to CPU, basically. So anytime a VM wants to talk to another VM here, and there's no path, it comes to the software kernel, right? We immediately know, oh, this vPort belongs on this switch. By the way, the only way to reach that is via a tunnel. So let me dynamically insert a vPort rule or an in-cap rule to tunnel that packet on that switch-to-switch tunnel, right? So the setup happened via software help, but the data path is in the hardware, right? To answer your question, basically, right, you were asking, what do we do with these flow insertion rates? This is where the flow insertion rate comes in very handy, right? That it's just an in-cap flow that I have to insert on the TCAM, right? And while the VMs are talking, that flow is active, right? The moment I get another VM wanting to talk to another VM and there is no entry, I can eject one of the flows that is not used and put a new flow in, basically, right? Now, slowness comes from, what is the hardware capacity and what is the software capacity, right? If your working set becomes bigger than what hardware can handle, you will see slowness, basically, right? But as long as there's a right ratio of working set in the hardware versus a bigger software table, you actually won't even notice this, right? And by the way, compared to running software tunnels, I really don't think you'll notice this. We did some performance data, and by the way, this is coming from ONUG, right? The Wall Street guys who have got their own consortium trying to drive this. The blue line here is what you see performance when there's no virtualization. The red line is 2 servers, a tunnel between them, and just one VM, right? Not many tunnels, just one tunnel to one tunnel. For different packet size, this is the performance you see. You move those tunnels to the switches, you're back down to literally line rate performance or no overheads performance. No CPU burning on the server side, just no performance difference. Keep in mind, by moving the tunnel on the switches, I've opened up the server world totally. You can run your Linux KVM without worrying about tunnels. You can run OpenStack here without worrying about tunnels. You can do whatever you feel like on the server, right? And obviously you can run vSphere and just manage your server VMs. All the compute here on the servers is meant for server VMs, right? By the way, these heavier boxes are capable of running full services as well. So your virtualized services can run out of here, basically. And we do offer full HA and so on and so forth. So you get service level HAs and so on and so forth, and distributed services and so on and so forth. I can go into some of these details.
So you just said let us do your VXLAN instead of NSX.
You said that, I didn't, but that's exactly what I said. It makes sense. It makes logical sense, right? And guys, this is like, look at it. The reason VXLAN came in was to solve a problem. So I'm not saying it was bad. What I'm saying is that this thing was a mess, right? The whole L3, L2 network and how the networking was done was a mess, right? So we went down to the server side. We said, look, I'm just going to use server software. It's easy to change the software, and I'm going to run tunnels from the software, right? But the mechanics of what happened there was a little bit interesting. First of all, the world I come from, doing anything centralized is a cause of immediate firing, right? So in spite of that, somehow these guys build central controllers, right? Single point of failure, can't scale, becomes an issue, and so on and so forth, right? Then too many tunnels, right? Too many servers. As you grow, it's an n-square problem. As you add one more rack, now the number of tunnels goes out of proportion again, basically, right?
Now, you guys are always making this same argument about the number of tunnels.
Yes. I'm making argument about tunnel performance as well.
But that's a different story. There we agree.
Yes.
But this is the same thing as saying, oh, imagine how many TCP sessions are running over this network.
No.
Yes. You don't see the
Let me
tunnels in
answer
the
your
network.
question very clearly. I kind of give this as an example earlier. I come from a world of server OS. I ran a team of people who had no idea how tunnels get built in the kernel. This is true every kernel. The kernel guys only know TCP, IP, Ethernet. All the offload for 20 years is built between TCP, IP, and Ethernet. We work with Intel guys, we work with all the NIC guys, how we do LSO, how we do LRO, how we do checksum offload. It's direct function of TCP, IP, Ethernet. Moment something comes in, all of that goes out of the window.
And we agree.
There is hear me out, hear me out. There is no offload to deal with the in-cap and decap in the server world, right? So the tunnel scaling starts mattering, right? Try putting 10 tunnels on your server and run the numbers, while at the same time, try running 100K TCP session from a dual socket server. You'll be able to run 100K TCP sessions without any issue. You won't be able to run 10 tunnels at line rate there. That is what I'm saying. And I did that code. Guys here did that code. We still do that. This is our life. I'm not kidding it. By the way, we are not getting dragged into this. I didn't start with this. Our customers are pulling into it. The data is coming from customers saying, why the hell are you guys not doing this? That's why we are slow rolling this. I had no desire to go and say, hey, these big guys out there, they're doing something wrong, right? We're just trying to win the market, basically. Customers asking for it, so we're going to go down there. Yes, we had to show the problem clearly. And that's what this slide is doing. I'm not one of the guys out there just beating Bush about, hey, he's saying it, let me just jump on the bandwagon. We're not the bandwagon guys. Please remember that. Coming back, sorry. You pushed some wrong buttons here.
Whatever.
So what ends up happening basically, right? There is real, if you look at worst case scenario, N square versus running tunnels from switch to switch, you're using the hardware here, right? You don't have to worry about the rest of the network. This is just like server world. You leave the rest of the network alone if you want to, right? But you're using the top of the rack switch, which has TCAMs, to offload the tunnels, and you run from there, right? It's really, hardware offload and 50:1 reduction, if you look at it. Typical world, what ends up happening, you have 40-odd servers in a rack, right? And if you are running tunnels from server to server, what end up happening here is that you are now running tunnels from switch, right? And that's end up being a lot lesser tunnels, hardware offloaded tunnels, you can scale. And there is a soft problem that it solves, the topology problem. The servers become clean. The server guy doesn't have to worry about the network topology anymore. The network topology comes from really the networking guy, right? Now, I apologize again. So, having said that, let's talk. What do you think is the problem with this?
Oh, just go on, sorry.
We'll have to talk over beer. So there are a couple of topologies that come into play, right? I mean, obviously we can run any spine, we can run any L2, right? And as long as top of the rack is under Netvisor control, we form a fabric around here. The fabrics are transparent to VLAN or VXLAN. And you can actually run this over L2. You can run this over L3 fabric. So you can have L3 coming from your BGP CMP from top of the rack, and your fabric is transparent to that. We can also provide the leaf spine architecture, where you have L2 at the leaf spine level, and fabric running over your tunnels. Sorry, in L2 you don't need tunnels. When you go L3, you can actually do tunnels, basically, right? The more interesting use case starts becoming this. At the end of the day, server guys want L2, right? At the end of the day, the VMs want L2, right? So what if we actually build a L2, L3 spine, a pod, which is L2 at the bottom, at a spine level, and we use VXLAN tunnels from the spine layer to connect these pods together. Right? Now, interestingly enough, your scale problem has actually gotten even better. Right? Because what ends up happening here is that inside this L2, if your orchestration software understands this a little bit better, try to fit a lot of the VMs into a same L2 pod, basically. Right? We need to create in-cap rules and use the VXLAN only when the VMs are spread across 2 pods. You need to scale more, add a couple of more switches, and add more tunnels across those. Right? So this model actually starts becoming a less, so to answer your question, this is the model what we are seeing in data center starting to pan out quite a bit. There are 2 models. There are bigger guys who are doing the BGP fabric to the leaf, right? And run on top of that. But typically these guys are non-virtualized, right? They don't have, Facebook does this for instance, and they don't have much virtualization in-house. What ends up happening is that you typically see more data center virtualization at a pod level. Here's my leaf spine architecture, and I can actually run my virtualization here. And anytime I need to grow on a pod basis, we just go another pod basis.